Okay, so the next result we want to prove is this inclusion lemma 1. So what it says is that if we have an object A of set to the power of C, then suppose we pick a subset A subscript E of A of E for every object E of C. And then also suppose that this collection of subsets is closed under S actions. So that means that for any arrow S from E to V in the category of C, we have that this function A of S is going to send every element of A subscript E to an element of A subscript V. Well, in that case, we claim that there is a object X which has X of E equals A subscript E, and also this object such that X of S is the restriction of A of S to A of E, to A subscript E. Okay. So in this case, we claim that there is an object X with X of E equals A subscript E, and X of S, the kind of action function of X with respect to S, is this kind of function which is the restriction of A of S to A subscript E. And also we claim that there's a natural transformation I from X to A where the eth component of I is just an inclusion function, which makes sense because X of E is A subscript E, which is just a subset of A of E. So yeah, we can have an inclusion function like this. But the claim is that together these components actually form a natural transformation. And moreover, I is a monomorphism. And so we have this kind of structure, and then we call this kind of monomorphism I from X to A an inclusion monic. Okay. Okay, let's prove inclusion lemma 1 then. So we let X of E equal A subscript E be this kind of subset of A of E, which we've described. And then, as I said, for any arrow S from E to V, we let X of S be this kind of function from X of E to X of V, which is really just the kind of restriction of A of S to these kind of subsets, because it's if we restrict it to this subset A subscript E, well, it takes all its values in A subscript E. X of S takes all its A of S takes all of, when we apply A of S to this subset A subscript E, it takes all its values in A subscript V by assumption. And so we can really think of this as just a mapping from A subscript E to A subscript V. And that's what we do. Okay, it's just that we call A subscript E X of E, and we call A subscript V X of V. So that's to set up. Now, our first thing we need to do is to show that this X defined like this is actually a functor. So it's clear that X of S has the right kind of source and target. It is indeed an arrow. It is indeed. And so, I mean, what we want to do basically now is we want to show that X is a functor from C to set. So in other words, we want to show it's an object in set to the power of C. So it's clear that X is sending objects of C to sets, and it's sending arrows of C to functions. And it's also clear that if we have an arrow S from E to V, then X of S is going to be an arrow in sets from X of E to X of V. So we just have to show that the sort of laws of functors hold. So one of them is that X has to be such that the composition x has to be such that the image of the composition of arrows under x is equal to the composition of the images of those arrows under x. So in other words, we want to show that for arrows r after s in C, we have the x of r after s is equal to x of r after x of s. So we want to show this kind of equality holds. So how do we do it? Well, these are just functions, so let's just show that they work right on a sort of general element of the source set. So let's suppose we have some theta in x of e. Now we're going to have that x of r after s of theta is going to be a of r after s of theta, because I said that x just works like a on things in these chosen subsets. And we can rewrite this, because we know a is a functor, so we can rewrite this as a of r after a of s of theta, like this. And then we know that this thing in the brackets here, a of s of theta, is going to be a member of a of v. And so that means when we're doing a of r on this thing, we can equivalently write this as x of r on this thing. And we can also, since we know that theta is in a of e, a subscript e. So, okay, how does this reasoning go then? Well, we can rewrite this thing in brackets here. Well, so how does this reasoning go? Well, we know that this thing in brackets here, a of s of theta, we know that that's going to be a member of a subscript v. How do we know that? Well, we know that sort of by assumption, we know that a of s is going to send this theta in a subscript e to a member of a subscript v. Okay, and we also know that a of r works just like x of r does on members of a subscript v. So we can rewrite this a of r of a of s of theta as x of r of a of s of theta. And also, since we know that theta belongs to a subscript e, we know that doing a of s on it is just the same thing as doing x of s on it. So we can rewrite this as x of r of x of s of theta, which is just another way of saying this is x of r of x of s of theta. So basically, we've shown that these functions here, x of r after s and x of r after x of s, these two functions work the same on a general input. So they're the same functions. So we have x of r after s equals x of r after x of s. So that's good. We've shown that that the law of composition is still preserved. The only other thing we need to do is show that the thing works properly with identities. So this is pretty easy. We want to show that x sends the identity arrow of e to the identity arrow of x of e. All right, so the thing is that x of the identity arrow of e is sort of by definition just the restriction of a of the identity arrow of e, this function here, to a subscript e. And since this is the identity arrow, if you have an identity arrow function and you restrict the kind of inputs, it still looks like an identity arrow if you discard the things that nothing gets sent to and restrict the inputs. So this is just going to look like an identity arrow on so when we restrict this function, A of the identity arrow of E to A subscript E, it's just going to look like a identity arrow of A subscript E. And A subscript E is just X of E. So this is just the identity arrow of X of E. And so we have this other equality holding here. And so this shows now that X is a functor, okay, because it satisfies all the necessary things it has to. And now for every object E of C, we suppose we have this kind of inclusion function, A subscript E, which is really just including this subset A subscript E into A of E. So firstly, we want to show that if we gather together these components, we get a natural transformation. So we claim that I is natural. So how can we see that? Well, we just have this naturality square here. Okay, so we can see that this is natural because if we start with a general element theta of X of E, if we go this way around, if we do I subscript E on it, it doesn't change the actual value of theta. We just consider theta now to be a member of this larger set A of E. And then if we do A of S on it, of course, we get A of S of theta. So that's what we get going around the top and right of this square. Going along the other way, if we take our theta and we do X of S of theta, then we do A of V, that doesn't change it. So we want, for this to be natural, we want to have this holding that X of S of theta equals A of S of theta. And that's exactly the case because we know that X of S is just defined to work the same way as A of S for these kind of inputs. So yes, we have that I is natural. Now finally, we just have to show that I is a monomorphism. So why is I a monomorphism? Well, we can use the Hom lemma. Well, we can use the mono-Hom lemma to get this. So let's just consider a couple of arrows, zeta and zeta dash, which come from Hom E comma blank into X. And suppose we have I after zeta equals I after zeta dash. And then, of course, we just want to show that zeta equals zeta dash, and then the mon-homo lemma, and then the Hom mono lemma will prove our result for us. So the thing is that given such as zeta and zeta dash, we can find E-type elements theta and theta dash of X such that zeta is theta under arrow and zeta dash is theta dash under arrow. So these are the kind of elements of X of E corresponding to these arrows, zeta and zeta dash, under the kind of Yoneida correspondence. And then since we're assuming that I after zeta equals I after zeta dash, we have that I after theta underlined equals I after theta dash underlined. And now by our natural lemma, we have that these give us that, and now by our natural lemma, we have that this is equal to I subscript E, and now by our natural lemma, we have that this is equal to I subscript E all under arrowed, which, and then this is equal to I subscript E if, and now by our natural lemma, we have that I after theta underlined is equal to I subscript E of theta all, and now by our natural lemma, we have that I after theta under arrow is equal to I subscript E of theta all under arrowed. And similarly, we have that I after theta dash under arrow is equal to I subscript E of theta dash all under arrowed. So we have that these two things are equal. And then we can just use the Oneida correspondence to sort of remove these under arrows to talk about these kind of elements corresponding to these kind of arrows. So we get that I subscript E of theta equals I subscript E of theta dash. And then since I subscript E is just the inclusion function, that just means that we have theta equals theta dash. And now, again, using the Oneida correspondence, we get that theta under arrow equals theta under arrow. And now, again, using the Oneida correspondence, we get theta under arrow equals theta dash under arrow. And that gives us that zeta equals zeta dash. And so we've essentially shown, assuming that I after zeta equals I after zeta dash, we've shown that zeta equals zeta dash. So now it's a sort of direct consequence of the mono-hom lemma that I is a monomorphism, and that's what we wanted.